Alright, so hello everyone and welcome back to yet another video on this AutoGrad series from scratch in C. So as you know that we were building AutoGrad from scratch in C, and our MHA, that is multi-head attention layer, failed because we had applied all the floating point operations there. And right now we need to transition to tensor operations to make this work, because if you see here, if I show you my previous function, it was multi-head attention forward, and we used here some tensor um, multiplication functions which keeps track of the parents and the function that have created these tensors q, k, and v. But later on in this code, in this script, you see we loop through the number of heads, and first of all we apply this dot product attention score to manually created tensors over here, and then we slice the heads from this big tensor, which was actually working well for floating point numbers. But in order to create a computational graph out of it, there was just not working, because we need to keep track of the computational graph and node tensors, right? So each tensor should be a node which represents some a particular space, some particular functionality in the graph, and then later on when we'll update these things, the gradients will flow back smoothly if you have all the nodes available. So the graph is breaking. It's just like a, you can say, imperative math sort of numpy sort of code, which exactly does what needs to be done, but it doesn't keep track of, doesn't build a graph for us, right? So the whole idea of using tensor operations to build a graph, and that's what we are going to do next. So I've commented out this code over here, and let's just try to build this MHA forward and see how things work. So for this, I'll be needing two important functions, that is tensor slice and tensor concatenate, because from the big tensor, let's say if we have 16 cross 32, for the sake of simplicity for dimensions of our tensor, we will be dividing these two head chunks. And by head chunks, I mean that for example, 32 will be divided by number of heads. Let's say heads are 8, so each head will have its own dimensions, that is dk inside transformers. And then this dk, we will use this dk to find the heads, and then once we find the head for q, k, and v, which is right here, their dedicated heads, we will perform scale dot product attentions on them, and then we will concatenate all of them, and then this will be our attention score, and then we will multiply this by wo to get the final result from multi-head attentions for pass. So if you have no idea what I'm talking about, there's a video of mine you can see in which I have explicitly explained how this multi-head attention layer works in detail and what the head dimension is. So right now I'm going to implement this for tensor operations to create the node of tensors. Each tensor a node in our computational graph, and let's see if things work or not. So let's go. So I'm going to pull up this file tensor.c, and the first function that I'm going to implement is tensor slice columns, and this should take arena, pointer, and actual tensor. Let's call it tensor x. And what else it takes? It does take column dimensions, and let's just call it dk. And what else it takes, we'll decide later. So int rows equals x shape 0, 1, and dimension would be, and output shape would be something like arena allocate. Let's allocate some space for it using arena, and what and dim times size of integer, because we have two integers in n dimension, that is rows and columns, and n dimension times size of integer would allocate output shape, and output tensor would be having shape equals, rows would be same, we know this, and we are slicing. So remember, if actual tensor x has shape, let's say 1632, output out tensor will be sliced version of it. and we'll have shape equals 16. Rows will be exactly same, and dk, right, which is the dimension along the columns, right? So this is going to be our out shape. So let's just say out shape 0 would be what? Yeah, dk. Fine. Okay, and that's it. Create output tensor now. So I think I should commit things. It makes a lot of sense later on to read this and understand, yeah, what was going through in my head while coding this out. So tensor, this will be tensor, create new, use arena, dimensions, and out shape. Create this for me. Fine. Core logic here. Slices the main tensor x and populates out, populates tensor out, right? So yeah, so what do we have here? Now here's the thing. um I have something like this. For example, 1 2 3 4 5 6 7 and 8, 7 and 8, let's say. And what else can I do here is something like this. Okay. Okay, let's take it here. Let's say these are all the values inside the tensor, and I'm going to slide it like this. So, right, 1 2, this will be my, let's say, first tensor, and then the next would be like this, and so on, right? So I need to have some starting address, right, and columns width, right? So columns width, that is available right there, right here. So let's just do one thing. um, what I'm gonna do is I'm gonna first comment this, and then let's just create a start. So float start would be x data. Let's use pointer arithmetic, using pointer arithmetic. So x data plus what? K times uh, x data k uh, dk. Yeah, so this will take all the elements of rows and dk. Rows are the actual rows and columns are dk. And I need int k here as well. K, I'll use this k over here, and then what? Let's just do through to find all the numbers. So r plus plus uh, 0c less than dk for column dimension. And print, no, not printf, let's just populate this out. Data r times dk plus c would be what? Start r times dk plus c. Should it be like this? Or should we test it first? Okay, let's just test this first. I'm not sure if this code works. Let's just test it over here. So I think, let's say I have rows, columns 32, dk equals 32 divided by 8, heads equals 8, and dk would be 4. So float start, or let's just call it data, or what, just call it data, x data plus dk, and okay, let's just copy this. Yeah, float. Let's just call it data, and this is also data. Okay, let's just first print it, and what? Uh, there's row. Yeah, k is not here. So let's say for um, okay, so no, not like this, not like this. Yeah, we can also do it like this. We can also do it like this. So we have what we're doing here, and this. Okay. Uh, R rows dk data times tensor create new. Okay, we're getting something. Um, okay, looks like we're getting something. But is this correct? I don't know. Let's just see. Let's just see. Okay, so now we need to populate this thing, and start is k times rows times dk. Yeah, this looks fine. This looks fine, I guess. And if you return out and just call this method over here, tensor, tensor slice columns A. No, you cannot call it like this. So let's just use int has equals 8. 0 while can we do something like this? So tensor out equals tensor a x k and dk. We have incremented k, so let's just increment that as well. Dude, 4 0, what is this? Mm, okay, so should we do something like this? What is calls? Calls is X shape. Wrong. 4 0. The shape should be 16 4, not 4 0. Okay, so let's just check what we are doing. Output shape is dk. Shows okay. Okay, so I think something is wrong there with our function. Um, okay, let's just use x data and stride. So let's just do it this. Can we do it this? X data r times columns plus c plus k times dk. Will this work? And is this correct precedence? Okay. So we are using head stride over here. So r times columns plus k times dk. And let's see if this works. Tensor create new heads 8. Oops. Wait a second. Yeah, man. That's correct. So I accidentally output set the output shape of rows and rows is equals to rows and dk. So that's why I was having problems. So let's just try one more time this previous logic and see if this works. Or should we? Um, okay, so this method is working fine. And let's just see one more time if everything is correct. I think we should add the value as well. just see. Okay, working, that's correct. And let's build the computational graph now. Build graph. So this is going to be if requires parents would be 1. Hmm. X and uh okay, fine. Let's see if it works. Something is wrong. Okay, so tensor slice columns backward. X. Tensor slice columns back. This is not OP. Oh yeah, this is outgrad. Yeah, something is wrong with tensor slice. It takes tensor. It takes tensor. Yeah. So tensor dot edge slice columns backward takes tensor. What's wrong here? Oh, fine. This function is working, right? Let's now implement the concatenate. Tensor concatenate. So tensor tensor concat, and it's gonna take tensor out, tensor a, x, and what? Mm, k and tk. Mm, so it just concatenates. Let's just write the main logic first for int less than dk. Oh, sorry, this is out data plus dk k times would be what? Plus c. So let's just see. Shape 0. Okay, so rows and dk is there, and k is also there. Will it concatenate? Return out and all right. So I think uh, we need to, or should we create this out inside this concatenate? That'll make a lot of sense. Should we create this inside or not? Let's just, if we create inside, I think we should create this inside. So let's do one thing. Let's grab all this from here. Yeah, and everything is else everything else is same, and let's just delete this, and what we have is x shape and x columns. X column is let's not create out here. So we have tensor. We need to create outside of the function, because each time we'll be concatenating. uh, each time we will be concatenating, and it will be creating a new out for us. Yeah, let's just quickly check. Let's just check. Okay. Okay, we'll check it later once we create the function. Let's just create it first. So let's take outside or inside. If we create it outside of the concatenate method, we need to keep track of the of its starting addresses, and let's see. So we have out, we have k, we have dk, Okay, let's just check this. All right, so you know what? After doing some R&D, I have come to know that something that we can do is we can store each head into some array of pointers, and then we can traverse that and just create a outside output tensor and then populate that. So something like that for concatenate. So tensor concat. There should be something called as yeah. So the obvious thing, the first thing is arena pointer, and then we'll have tensor heads, head chunks or whatever, and int num heads. So we can traverse these heads, head chunks to get each head and then concatenate it outside. So let's just define rows and columns. Essentials rows equals let's say heads. All will have same shape, shape 0, and same for calls 1, and m equals mm, and m, and out shape would be something like this. So out shape 0 would be what, rows, and so out shape 1 would be what, heads times dk. Wait a second. Yeah, heads times, let's say, columns, and this will be like 8 multiplied by 4 equals 32 for now in our case. And let's just create out tensor. So this will take arena and shape, and let's just populate this now. So if graph, so if let's say okay, let's see if we need to build the computation graph for this or not. Let's just write the main logic, core logic, and this will be like for k is less than heads k plus plus, and for rows are plus plus, and then for less than, let's say, and this will be like out data r into columns plus times. Okay, so I think uh, let's define them explicitly. So out calls would be calls times what, heads, and this is our outcomes, maybe. What is tk? Cons plus c equals what? Yeah. Oh yeah. So now the issue has resolved. So we need to define head here. So this would be heads times k, and let's just rewrite this loop. So we have the head tensor, uh, like let's say head chunk, and then we go for rows. Mm, okay, so the heck is wrong? Okay. All right. So uh, this is our concat method, and let's just register this over here. Tensor x. So tensor arena a, and what else it takes? Yeah. So list of all the heads, and it will be tensor heads and what? Yeah, so this is actually our concatenate method, and next will be uh, adding these functions inside here. Instead of these slicing and concatenation operations, we'll be adding the actual slice tensors and concatenate tensors. This is actually the difficult part, which we have done now, and I will see you in the next one, in which we'll be actually integrating this R with our MHA4 function, and I'll see you then. Take care.